We hope you are all doing well and are staying safe. We'd like to welcome you to today's webinar. Dr. Moshe Ben-Talila, who will be conducting the session, has been the manager of VisiMix's customer support group for over 14 years. He has both a BSc and an MSc in chemical engineering in the field of reactors design provided by the Technion, which is the Israel Institute of Technology. He was involved for more than 15 years in technological transfer as a pilot plant manager and as a project manager in an API company. In conjunction with this, he has his PhD thesis in the chemistry field provided by the Hebrew University of Jerusalem in Israel. His dissertation describes the application of practical methods for scale-up process in a specific field in the chemical process industry to show its validity to the chemical industry. He was part of the team that wrote a syllabus for a BSc degree program in pharmaceutical engineering, contributing to the relevant studies for the chemical engineering profession. He was a team member of a committee that wrote the program syllabus for the pharmaceutical engineering BSc degree program in Israel for the Azrieli College of Engineering in Jerusalem. During this activity, he programmed and built a complex of student laboratories for process engineering, biotechnology, analytical laboratory, and pharmaceutical technologies. In this college, he is also a lecturer in reactor design and principle of fluid mechanics. In this session, we will talk about the influence of mixing in the process, focusing on the simulation cycle. The simulation cycle proposed by VisiMix includes a well-based comparison of the performance of mixing operations performed in mixes of different designs, different scales, and/or different regimes. This comparison takes place with respect to each unit operation, which is the technical target of the mixing operation as defined by the user. The results of different VisiMix projects and comparisons are then organized in the form of sets of tables and graphs containing values of VisiMix input and output parameters. During this webinar, please feel free to write any questions in the chat box. We will try to answer them during the session or afterwards via email. Enjoy today's session. Moshe, the microphone is all yours.
Okay, so thank you very much for the introduction, Marcy, and I'm very happy to meet with you again and start our normal cycle during the year to have a forum and presentations about how to implement this fundamental part of mixing in the company. I only will ask for Marcy if there is anyone in the lobby to enter it inside, okay, because people are entering during the meeting. If you are able to do it, I will have or Aldo and one of the VisiMix team. So thank you very much to be here. As Marcy explained to you, we are talking about today about the influence of the mixing in the process. That is normally our issue. And today we'll talk about simulation cycle. That is some kind of integration of a group of VisiMix products that provide to you a capability in a very fast and simple way to put in one page all the main mixing parameters that maybe can influence your process. So VisiMix as a company, for people that don't know us, VisiMix is a company located in Jerusalem in Israel that develops simulation of the mixing for the industry mainly. And today we will discuss about why we need mixing in different steps. And we would like to hope that we are passing this coronavirus and we prevent ourselves. We are here. As you remember, 1 or 2 years ago, I wish you a lot of health and more that we need you. You are people that are connected directly or indirectly with this solution to the world. So we like you to be healthy and prevent for any problems that will not happen you. So today we'll talk about the company few minutes, the motivation, why mixing is important, and after that we'll through the examples try to touch why we need this cycle, why we need the capabilities to show in a very simple way what will happen in the lab, what will happen in production, or why we are in the production, or how to go to the lab again, how to go through the design, all of these idea, but try to connect in one integration, in one way that will give us a capability to have a comprehensive idea of what we dealing with. So VisiMix, we are located in Israel, is a unique software because it's based in physical models that have been developed for exterior vessel equipment. So the model is our model. We combine the solution of momentum balance to know the velocity of the flow. In other hand, we have a lot of information of experiments that we perform in order to support this model, and we have our experience. The combination of these three provides to you a number in the output of the software that will give you a representative number for the process and for the parameter you're looking for. So it is not only a pure or cool number coming from some mathematics or not only some empirical data that we get. It's really a combination of both and our experience to try to release a good answer. So this is about VisiMix. We established in 1995, and during this time until now, we develop every 2-3 years group of products that we know the market is looking for, and try to solve different kind of problems in mixing, from the fundamentals about turbulent and laminar, and after that some kind of analysis, VisiMix, VisiExcel, or 3D representation of the flow, or analysis, or different kind of installation of the equipment, like different impellers in the same shaft, or rotor stator, that is high shear rate, or off center. So every a couple of years, we are releasing news according to the demand on the market and our capabilities to provide the best results. And the motivation to use this kind of calculations and more to try to have a comprehensive idea and integration of all the activities is coming from this picture. If you are working in this field, you are feeling that you need to answer these kind of questions about the parameter of process, what is a good process, what is the robust process, what is a safe process. But if you summarize all of them, you can have one question, a very simple one question. What will happen with my process in the next step? I did some work. I know what happened in the lab, or I manufacture my equipment in some facility, and I need to go to the next step. For instance, to transfer the process to other site, or to go scale up from the lab. And we need to know what will happen, because the company is asking me, it's our responsibility to answer the company what is expected. This is our goal. In the point of view of the management of the company, it should be very simple, because you have some base, you succeeded in the lab, or you want to reproduce what you have in the lab, even if it is not exactly perfect, but it's something that you want to progress, the decision of the company. In other hand, you have some good results in one manufacturing place and you want to go to the other side. So from the management point of view, if you succeeded and you are not changing the raw material quality and you have the same process, you have no problem. It is very simple. Go ahead and we'll succeed. But in the professional point of view, it's a little different. You know that when you are changing dramatically the geometry, all the environment that you are providing to your materials to progress in your process maybe are different, are not, this environment is not good for the process, or a little deviation of it will generate some operational problems or yield problems, or quality in the final material or in the intermediate that will not give you a capability to generate the expected results. So you need tool and capability to answer the questions. And here in this step, the main change is coming from the equipment and the integration between the equipment and the process. This is our goal. For this, we are here. And this is what we need to answer, and this is expected from the company that will provide. With the software, of course, we're able to calculate at every place what is going on. And if we have some knowledge from the lab, we can take in advances in order to advise the design and the production and to justify what we are doing. If we are working in the production, we have a capability to, from this, have some idea about the design that we have in other place, or we have to buy a new company, or if we know about the production and we have some problems, we need to solve some problems, we can come through the environment we generate in the production, through the software to generate the same conditions in the lab in order to coordinate between the equipment, the process, and of course the knowledge that we provide to the company. This is the main idea. So what is a good mixing? The answer is automatically good homogeneity, high velocity, high shear rate. It is good when the mixing is our goal, but we are in the industry. And when we are in the industry, we are dealing with different kind of points. I want to give you some example. A company, very big one, did some work in life science, some process, a chemical process. And for some reasons, the equipment broken, was not good. They replaced the equipment with a new one. And during they contract a company, engineering company, and they design all the equipment and install and run. It was running mechanically perfect. But when they ran the process, it was a problem. 1 minute, please. Sorry. Sorry, some problem with the sharing. 1 minute, please. I will check. I will check. 1 minute, please. Some problems will happen here. Okay, we had some problem with the connection. So I will, with your permission, repeat again some of the points. Sorry for that. I hope now you can see my computer. Okay, so I'm going regarding the company explained, so I will not come back to it. I will enter directly for the technical part. The motivation of the use of these kind of activities is the following. When you are working in this step, the connection between the equipment and the process is fundamental, and you are generating some environment, okay, some environment to your process. So if we want to answer about what will happen in the next step, that this is a summary of all of these questions, in the point of view of the management, it should be very simple because you succeeded in the older equipment or in the lab, so you don't need to reproduce. But in your point of view, you understand that when you are going to the next step, even if you're changing the geometry or you're changing the size, okay, the size of the equipment, you are providing different environment to the process to progress. So the connection between the process and the equipment should be clear. And with your knowledge about the process, you will be able to implement what is the environment required for the process. This is our job, and this is the company expecting from us. If we are able to understand from the lab what are the conditions to provide to the next step, we will be able to advise what happened, how to design, how to operate in a good way, to how to generate good results and justify. Or opposite, if we are working in the production and we have to do some troubleshooting or to transfer the process to other side, we can come from the production through VisiMix to the design, to the R&D, or to justify why the equipment, why the next step will be good, or why we need to do some adjustment to generate our results in a good way. So the point is, what is a good mixing? And as you can understand, good mixing is not only related to high homogeneity, velocity, or shear rate. It is good when the mixing is alone, but we are mixing, and when we are mixing, we are service. Our important point is the process. We are serving the process. We are generating conditions in order to get a process that have a good productivity, a good yield, and we have no problems in the operation, and the quality is okay. So an example, explain us about it. Company that has some problems in the equipment, and the history was that they have a good equipment, but it was broken. So they changed the equipment to a new one by a subcontractor, and it was working perfect in the point of view of the equipment by itself. The mechanical equipment was okay, but when they start to run the process, was some deviation, was no good results, the quality was not okay. The process was a chemical reaction in some bits, some porous bits, and they thought that, okay, they have some deviation, some fine tuning will generate good results. The point was to take in consideration that oxygen was not good for the process. It's some data that they didn't have at the beginning in the subcontractor, they had in the company, but not in the subcontractor. And what happened is when they tried to generate this fine tuning, it was not successful. They didn't have a capability to catch the point. When we calculated with VisiMix, we found that it was impossible. Why? Surprise. In the older equipment, the solids were not well distributed in the media. So the bits were moving well, but only in the bottom of the tank. Where the change to the new equipment was designed in the way that the solids that, were well distributed in the tank. The meaning of this distribution of the solids was almost homogeneous. But what happened when you have solids homogeneous in your new tank? Part of the solids see more oxygen from the heat space. And now you generate an impurity and hydrolysis and generate bad results. So here opposite, we thought that we need homogeneity because we're missing homogeneity. We designed for the solids because it was the main part of the process, but it generates bad results. And the point is exactly it, how to connect between our knowledge and the design or the operation to generate good results. So in this case, the company understands two main important points. The first is you need to coordinate all the data, and you need to control the process. You don't need only to pass some procedure to the subcontractor that will do, because you know more than them. And second one, once you have the equipment, you need to be sure that you are meeting the specification you have. And in this, no connection between these two fields, the knowledge of the hydrolysis and the results, they lost about 6 months and 1.2 million euro in the installation. So this one point to understand why we need it, okay? So you see here all the equipment, a very big loop here of flow that keep the material in the bottom. The new equipment was better distribution, but some of the equipment, the material is meeting the oxygen there. Okay, so we understand that we need to understand what is a good mixing and not always homogeneity, and we need to connect between them. So the proposed method that based on it we will do the cycle and the integration is to try to connect between the equipment and the process even at earlier stage of our project. And it was based in my own experience when I was pilot manager. We get many problems in the transfer from lab to production. We have no pilot, and big problems. We take many batches in the production to generate good process in the production step with no how to spec material or operational problems, etc. So what we did is to think in other way. Instead to try to succeed at every step, to calculate with VisiMix what will be the conditions that we will be providing the production step and try to adapt it in very early stage in the R&D. Or to understand what we had in the older facility, ask the data from the new facility and try to implement there conditions that will be similar that we provide when we generate good results in our older equipment. So the explanation you can see here is very simple picture that I show every meeting because it's for people that don't know and it's very illustrative here. We have equipment with solids in the bottom and a pitch pedal. And let's say you are in one equipment. You go to other one by let's say I fit some buffers in the same stage, or maybe we are going to other equipment and you have different hydrodynamics. You can see how dramatically is completely different the solid distribution. So my process is different now. The interaction between material is different. And maybe there will be the reason that we have deviations in my process. So our idea was to catch it at the beginning of the way or in very early stage way in our project. We need to transfer process from lab to production or from site to site. Let's understand what will happen there. What will be the conditions there, and let's try to simulate in the lab to generate some data or to looking for in the experiments we have, on the experience we have, what will happen at these conditions with my process. And this is the cycle that we like to operate. So the methodology that explains sometimes is many times is to understand what happened in the lab or in the other equipment, calculate with the software what will be the mixing parameter that we will able to generate there, and after that to implement it in the lab on the other equipment or to combine between them to understand how far we are between them. And after that, after we are doing it, that we have some connection, we have some zone that is connected, we will be able to have a final design, some implementation in the older equipment, the new equipment, and we will have many important points, a model that explain me what is the environment that will generate good results. This cycle we'll try to do in the software. We'll try to take data from the lab or from the other equipment, calculate what happened in the next step, go ahead if we go back and we have some doubts about it, ask questions, and after we are doing this cycle, and we provide you how to do it in the software, we will be able to, okay, let's go. Now we are sure, we're relaxed, we understand that we know what is the environment that is good for my process. So it's here you have all the steps. This is a methodology that was part of my PhD. Know the mechanism of the process, calculate the mixing parameters in the next step, use the lab or the other equipment to match between these 2 points. If you have many parameters together, try to do some statistical design of experiment, even in the software. You don't need to go always to the experiment. In the software, try to generate enough a zone of parameters that give you an idea about the trend. And after you have it, prove it. It is important to prove in some way in the lab, in the production, the other equipment, etc., and generate the final design. This is the way that we advise, and we have, of course, a lot of public papers about it. In the last year, 2 years ago, we released about 3-4 papers about it, 2 patents in some specific field. And we invite you to come to enter my name. You will find we have all the mixing model, all the VisiMix model in the name of Dr. Kokoto for Professor Braginski, that they develop, of course, the software, and we are very happy to be there. Someone asked me, 1 minute, please. Ask me to take it out. Okay. Okay, let's progress. Now, and this was the curve when we start to think about this implementation, how we take down the quantity of problems that reduce dramatically when we start to think in this integration form in the company was I was pilot manager. In order to do it, we need to take in consideration some mixing parameters that are important to understand. There are many of them. I will not cover it in this brief presentation about it, but you need to think about levels of mixing. We'll talk about macro mixing. Let's say the integration of the mixing all the time. How long for it will take me to have a 99 homogeneity? What will be the diffusivity in all the tank? What will be the heat transfer, the mass transfer for different phases in the general all the equipment. After that, we need to think about zones in our tank. We have around the impeller, we have around the wall, we have in between, and how many times I'm able to change the volume or to move the volume in my tank is generate zones that are different in conditions. And we need to think that we are generating fluid elements that are interacting between them, and the time of this interaction, it will generate another level that is a micro mixing. So all of these levels are working together, and every one of the levels will influence in different ways the process. Okay, if we are doing very fast mass transfer, okay, maybe we'll include in some crystallization solvents that are no good in the crystal. If we are doing a very integrate point, but we have the average is some diffusivity, but we have around the impeller 1,000 times more, and my process is fast process, maybe we need to have a drop or semi-batch and drop into the place that is very high disperse of material for fast velocity, and we are controlling our process. So you can understand that we are talking about the integration between different levels, because mixing a multidimensional phenomena that we need to take care. And all of this happen at the same time. Okay, so we need to combine of these parameters. So it's only a brief idea. Of course, if you want more about it, we can discuss for every company. And some examples about it, what showed to you the solid liquid, but some examples about it. A reaction, for instance, if we have some salts in water and we feed HCl, if we have a good mixing, so we spray the HCl well, we will have a material that will have no color. And if we feed HCl with very bad mixing, so the spread of the HCl in the tank is not so good, we'll generate iodine that is a color material. And you can see here in this experiment, okay? Sorry. Yes. You see in this experiment where we don't have mixing, what will happen when we feed HCl with no mixing? You see here the color and the eddies, okay, very big ones, okay, because there is no moving. You see the color. If we are doing the same process now with mixing, okay, but from the upper side with low velocity, take care what happened here around the pipe, okay. You will see now a plume of color coming. Okay, you see now, if you see now, you see color. Okay, so we are not spreading well, better than than without mixing, but continue to have color, and you see all the material is with color. If we take now the HCl close to the impeller at low RPM, but you will see now, we will see a light, less color, while continue to see some color. You will not see a plum here, but you will see here that the color is a light, a little more than the normal one. But if you go to the last step and you are doing fast velocity and close to the impeller, you see that there is no color at all. So we need to understand that in different conditions, we will be able to generate different results. And this point we need to catch during our loop, during our cycle, to provide good results. So of course you are able to represent it in VisiMix, okay? And to generate here the difference between two completely different operations, how the curve is completely different, okay? How it's very fast here, very low here. So here you will not generate the hydrogen, here you will be generate the iodine, sorry, no hydrogen, the iodine. Okay, for liquid-liquid mixing, if a company in Dallas that did a very good job about it, they add some process and they need to have two phase drop into the liquid phase, into the oil phase. And what they did, of course, they measure the drop size again and again, and they try to generate the same forces from rotor stator in a big equipment for the laboratory one. And they measure the drop size, 290 micron, and when they use the software, they calculate 282 micron. Okay, and you see that they need some parameter of connection between the coalescence between drops to generate the one big drop, or to break up. This admixture value is something that they need to calibrate. With the software you can do it. And once they come to the next step, you see that at every different velocity, they generate very good results. Okay, you see here, very good results. So they found a good connection. So what I want to show to you here now is what happened in the liquid. If you're not doing this kind of experiments, and for instance, you feed kerosene in water in some equipment, you can see how you think that maybe you are doing mixing, but once you are operating in different conditions, it will completely give you completely different results. You see here kerosene, okay, in the top, here kerosene, okay, and you have here pitch pedal and rotor stator. If I raise the RPM to 200 RPM, you see here no connection between the phases. Kerosene up, water in the bottom. To 200, we have completely separate phases. If we increase to 400, what will happen now is that we are generating drops. Okay, it's good for a process that we need to separate phases. It's good because once we stop the mixing, okay, we have here the drop size. Okay, we calculate with the software. But when we click stop, what will happen now is we have separate phases. So it's perfect for process that we need to separate phases. It's very typical in synthesis procedures that you need to separate phases to clean all the phases, etc. Now, if we go to 400 RPM, but now after we generate our representative time, it's about 5 minutes, and I apply high shear rate with the rotor stator that I add here, what will happen now? We apply the rotor stator, high shear rate, 2 orders of magnitude more in the shear rate. What you get, you see, wow, now in few seconds, you see that we have very, very small drop size. And when we will stop the RPM, what will happen here is that we will not have phase separations. Now, it is good or no good? What is good means in here? It is the same equipment. It's depending. If we need separate phases, it's bad what we did now. If we need emulsification, it was bad what we did before that. So it's depending on the process. So we need to provide conditions to my process. And my job is to connect between them. For this, the software was defined. If you remember that we talk about the connection between the processes, you see, for instance, in crystallization, we have in our website, in our software, in the help, a complete connection between the parameters that are important to take in consideration for every unit operation. In this case, is crystallization. So we explain our customers what is the meaning of every parameter, how it will influence the process. We are doing it in our ongoing support for every process that you are doing. We have basic training, follow-up, sitting together to discuss results, adjust some problems in the feeding data on the results, and we're sitting together. It's part of our customer support. So take care that this knowledge we want to provide you as a customer. Okay, so use it. And let me progress. Okay, this I will not cover now. And the last point that I want to provide to you is to open the software and give you some idea about it. So this presentation will show to you, we have another 3 examples about what mixing is important, okay? And some new release, all of this you will find in the presentation we give to you, and all explanation about all the products we have. So what I will do now, of course, I will stop the presentation because what we have here we will send to you is all the explanation about the products, and this you will be able to read by yourself. And you have any question, please contact us. If you want some specific training or a specific meeting to your company to show, we will of course very happy to do it and explain the use in your specific application. So for this part of the meeting, we will stop. Okay, only I want to give you thank you, and before the thank you, to thank you for your attention. And now what I will do is I will open the software and do this the complete cycle that I discussed before that. Okay, so I will open Turbulent. And if you remember, only to remind people or to show people that don't know, I will do a brief the feeding data. Okay, so I have project new, and I want to go, for instance, 1 liter. Okay, equipment. I save in my desktop the name. Let's say I have a flask in the lab with no jacket, only to save time. And I have, let's say, 1 liter. The diameter of my tank is about 100. It gives me automatically the height of my tank, and let's say that my process was done in 0.7 liter. Let's say I have 2 buffers like this, like temperature, another one. The width of this buffer was 10. The distance from the bottom, let's say, was 20, and the distance from the wall was 9 feet, no? And 9 meter, in millimeter, was 5. Okay, and the typical equipment, pitch pedal in the lab one was enough for us. Of course, we can do multi-stage, different stage, all of this we can do, but in simplified way, we have pinch pedal. Let's say that my diameter of this pinch pedal is about 50, and we have 4 blades, 45 degree. The width of the blade is 10. The distance from the bottom is 20. The rotational speed, let's say, in the lab, very important, high velocity, because it will not generate enough intensity that they will generate in simple weight in the production step. And the motor power is not important here. In the production is very important. Here is not so important. It's only the motor we have in the lab normally is enough. And now we need, after we feed all the data about the geometry, the geometry of the tank and the operation, we need the process. The minimum data we need is density and viscosity. So we use, for instance, density. I will use water in this stage only to save time and simple way, but we can fit every viscosity we want. And once we have this picture, this is my lab. So what we can calculate in my lab, all of these parameters, hydrodynamics, many parameters, turbulence, many parameters, mixing, remember 3 levels, more. And after that, for every unit operation, we can calculate the solid distribution, the drop size, the gas liquid, a reaction, a heat transfer in different ways, continuous, not continuous, all the data that you need in order to progress in your process. Remember, in help, as explained before that, you have all of the parameters that are important for the scale-up, that are controlling your process. Every table here explains to you the parameter, where it's located, and what is the meaning. Of course, the meaning of this parameter will explain to you when we are working in the training. But you can see, we'll scroll down, you see solid, liquid, solid, or emulsification, crystallizations, you see all the parameters, okay, dissolution, liquid, heterogeneous reaction, gas, liquid, etc. So we have here all the information and the experience that we want to provide to you. Okay, so we are in the lab. We can characterize our process, so we can calculate, for instance, immediately the hydrodynamics, to see fast response. We can calculate some power per volume distribution. Take care, you see, I explained before that. The average is so far from the high and lower that we need to take care about it. It is not homogeneous in the point of view of flow. Of course, you will reach homogeneity in the concentration, but the diffusivities are different in different places of the tank, and it is very important to take care when we are trying to control our process. And of course, mixing times are different. But you see, I click get results. If you want to change any parameter, you can come to here and change. For instance, I go to 550. I click OK. You see how fast we change the results. New results we have here. We can here calculate the flow patterns. We can see these flow patterns in 3 dimensions. Okay, if I click the 3 dimensions, you can open the viewer of the 3 dimensions. What you will see, this fluids element that you are generated in your tank, how it's moving. It's very fast, so you can go down. You can reset and set up the inlet according to the place you want. So this fluids element from the bottom, I want to see and to check. This is from the top. I want to see and to check. And the others, I can put, for instance, this one above the impeller, this one close to the impeller, what I want. And when I click OK, I will see how my fluids element are connecting. In this case, it seems to be a very good connection. Remember, it's not telling me if it is good process or not, because we need to connect to my process. Sometimes it's very bad, sometimes it's very good. But you can see these experiments, and of course, every new conditions you can up and up see all of them together. So we finished to see, for instance, the hydrodynamics, the mixing times, the energy per power per volume. And let's say I want to fit some solids. You remember our example about the solids. I want to see what is the actual distribution of the solid, because I think it is critical for me. So I click here. The software will ask me new data. For instance, now separate between the liquid and the solid, because we need to know what happened between them. So we need the pure data for everyone. So this is the density and the viscosity of the liquid. Let's say we have 10% of solids in my tank, and the density of my solid is 1,500, and my particle size is between 100 to 300. Okay, this is my process. When I click OK, I get some notification about the deviation of the initial data. I can change or not according to my decision, but you can see here the solid distribution. You see here is the bottom of the tank, and this is the top of the tank. And here you have the relative concentration. That is a local concentration divided by the average concentration. The meaning of this, that in the bottom of this tank, we have 10% more material than the average, and it's going down to less 10% in the top of the tank. Okay, good for us. Let's say this is good for my process. I'm happy with this. Or I want to reproduce it. I want to go to production and to be sure. Or let's say it was one equipment, I want to go to the other equipment. So what to do now? We provide to you a guide. Not only try to do exactly the same. No, what is the mixing parameter that control the process? In order to do it, come to scale up, scale down. It will open a window, and in this window you see the data from the lab. You can set up what is your target. For instance, my target is around 6,000 liters. Okay, it gives me some diameter for from geometry similarity. Okay, some optional diameter that normally it will be around it in the production step. And it gives me a capability to fix every mixing parameter that I want, okay? And it will give me the velocity that I need to apply in the next step in the big equipment to generate the same, in this case, maximum shear rate. If you were looking for the maximum shear rate, you see it's the same. But the other way, and the very interesting one way, is here. If you are dealing with solid liquid, and the solid liquid is important for you, if you click here, the software select to you which parameter is controlling this solid liquid distribution, what will be the velocity advised, the velocity that you need to apply in the 6,000 liter equipment. So this is the best prototype because it's based in geometry similarity. Once you click OK, the software provides to you now, let's say, production prototype. It is the best production prototype you can have. Click Save. You have a new file with big size, okay? And where you will calculate the solid distribution, you will get exactly the same results. But you see now, if you apply there, the solid distribution will be okay, but here you will have some solids in the bottom. Oh, this is a result. This is not a mistake. This is a result. Now, What we need to do, you see this is the same distribution of solids. What we need to do is to avoid this problem about the solid liquid. What will happen with the solids in the bottom? One way is to change the RPM. For instance, I go to, let's say, 40, okay? But, okay, we have other problem with the mixing power, but we don't have problems about the solid distribution. We have no solids in the bottom, and we have 8% instead 10%. It seems to be very, very similar. But you can tell me, okay, but my equipment is not like this. My equipment in the production is not geometry similarity. I don't have exactly the same geometry in the lab like the production. So no problem. You can come here to clone, and you are generating the option one of the production prototype with the same data and change your equipment. For instance, now you go to the equipment that is elliptical in the bottom, okay? And the inside diameter was 1,900 and it was 6,000 liter, and you want to feed 4,500 liter in your tank, okay? And let's say that you have 4 buffers, no 2, okay? And let's say that your impeller now is not like this, is lighting. And the diameter of this lighting is about 900, distance for the bottom 450, and you are able to apply 120 RPM, no more than this, okay? This is the maximum one. And you have a good motor, okay? So now this is the real situation. What you need to do is only to come to the solid distribution and to see, oh, we have better situation. We have 5%, and we have no notification about the solids in the bottom. So it seems to be okay. But let's say you don't know, maybe 5% is very good, we accelerate another reaction. No problem. Come to your original one, let's say 50 RPM, come again, do your job. Solids in the bottom, no good. Let's go to 70. You see, I'm doing I only change, click and get results. Okay. You see now, oh, I have no problem with the solid distribution. We are 8%, very similar to the prototype. We have all of this ready to use. Now I want to see all of this together in one page. Go to the process analysis and bring all the files that are containing data that are representative for your process. And when you click compare, the software will bring you in one page the main important parameters from the 1 liter, from the prototype, and from your option. It will compare between the main important parameters, or if you want to see all of them together in one page, you can see all of them together. Now you have all ready to use, because you have all of this data, you have all the options, you can go up and down. Of course, I can come now to my software. I will double click in the best prototype. Okay, let's say I am the production one. I want to go to the best prototype, this one. And I click there and I want to go down. No problem. 6,000 liter, let's go to 0.01. To 10 liter, no. To 1 liter. Okay, good. Let me, okay, I did a mistake with my computer. It will be possible, okay? But 10 liter, let's say. I can go to 10 liter because I have some troubleshooting. I want to keep fix the same solid distribution. Give me all the results, click OK. And now you are in 10 liter. Calculate the actual distribution. You see it's exactly the same. We have no problem with the solids in the bottom. And again, you can do the process analysis. So you can do all of them, this cycle together. You have all in front of you. You connect between the mixing parameters that are controlling your process, and you have complete idea about it. Once you will do more deviation of the velocity, deviation of the solids, etc., you will be able to catch the main important point, and you will be able to provide the company the answer of the question that you are in charge of. It. It's your responsibility. The company is waiting for your answer on this issue. The point is to have a tool to do it, that it is a confidence tool, like many companies working with us. Some of them are here, and I'm happy to hear you and to see you here as a participants. It's always nice to see you again. And only implement the knowledge that you have on your process. Of course, you are unique because for this you have your projects, your products running and your projects, your processes. You need to bring the environment to generate good results. And we would like to provide to you in a good way all of these results together. The last point that I maybe didn't share with you is that it is able to, of course, to go to Excel. If you give some name in Excel, okay, we are, of course, able to open it in Excel. And of course, we have another kind of way to transfer data, but this is one of the ways. Okay, this is the, I think, the more optimal one, because you have all of this in front of you: the results, the basic results, the data of the equipment, all other data that is important, the mixing power, mixing times that are controlling these solid liquids, okay, the action and distribution of solids, and all the data together. This is in Excel. You can manage it, generate your reports according to what is required for you. So these are the wanted to show to you. Sorry for the first span. This is the first time that we are using this platform to generate webinars. So the first 10 minutes that you didn't see the presentation, I apologize, but I hope we succeeded to give you a good background about what is possible to do, and we're very happy to provide you more information about it. We have here someone that raised a hand, Oleg. Maybe you write in the chat. Oh, I will read the question from the chat. Okay. Of course, the first question that we are not you cannot see. Okay, we solve it. Okay. Thank you, Alberto, about it happening in the best families. We're happy to be in family with you. Question. Okay, Cliff Coward, nice to meet you. The question is, how do you effectively simulate really poor mixing in the laboratory? See, it's happening, and it's happening faster than we think. For instance, if we reduce the velocity to 150 RPM, the software will give you that you are in the laminar stage, laminar region. For people that are working in turbulent, it starts to be pure mixing because the complete we have no good transfer of material, and we are completely different mechanism of transfer material, and it will generate maybe a big deviation in the conditions. So this is one way. The other way, as you can see, if I increase or reduce the velocity and we get solids in the bottom, but 40%, 60%, and in my lab I did 2%, okay? Now it's not good. Sometimes it's not possible. Sometimes the limit of your equipment in the lab or in the production are not connected one to the other one. So we have no other way or to use a different equipment or to go to the next volume, okay? Sometimes when we are working in half a liter, it's not enough. When we go to 2 liter, it's okay. Many parameters we need to coordinate. It is our job, yes. In this field, we need to discuss in different language. People in the lab is discussing in different way that in the production, that in engineering, that in the QC, and we need to coordinate all of them together to generate our results. So this is the answer about really pure mixing. Yes, it happened. It happened faster than we think. We think that we have a good mixing, and I show in the video how a different in liquid in a 200 RPM or high shear rate, we have completely different results in the mixing. This was your question. Mr. Nissen Penny, do you have any simulation that look at moving circulation parameter to reduce recycling high pigment overall? Yes, we have. We have in our website a simulation about it and an example. We're very happy to connect you, Mr. Penny, to Mrs. Penny, sorry, to discuss with you. Please contact us, me or any one of the team here by mail, and we're very happy to explain about it. Oleg, hi. Thank you for your presentation comprehensive. Thank you very much. Penny, again, thank you. Okay, can you please share slides? Of course, the record, I am recording it, and the slides we will share, we will, of course, edit a little in order to, we had some problems here, and we will send you a presentation and edit the video together. You will see in our website, and you will get a link for it. Hi, comparing this versus finite elements, which is more accurate? See, Mr. Ben, okay, our models are based in a combination between solution of differential equation by numerical methods, but the solution that we get in the mathematical point of view, we compare with the collecting data what we generate by self to the model, and we compare with other papers that were published about it. So, and it was done for stirred vessel. So the model is for stirred vessel. So in this field, a specific field that we talk about mixing, we are very confident that our results are very representative for you. Of course, this was specific knowledge during many years developed in this team. Of course, in this place, we feel confident that we're able to provide good and relevant results more than any pure mathematical calculation or pure empirical results. Okay, but of course, you are invited to contact us and we'll discuss more about it. Oh, Hiram, how are you? Long time we didn't hear from you. I'm very happy to meet you again here. Can you provide power, or no? We are not providing power mixing. As you know well, there are no models that are a product, industrial product that you can use in simulation on it. We have some experience about high viscosity. If you have a little, some liquid there that you can generate some kind of continuity of the solids there, maybe we can use the liquid, the laminar, but of course it is not the default. Okay, it's something that we need to elaborate. But very happy to hear you and to see you here. And Oleg, how could our company get Monstrile? The Monstrile is there. You can download from our website and you can see there. The best to you, Mr. Oleg Ruskin, contact us. What we are doing normally to give you some reports. So if you provide us some data, we show to you how we feed this data, what we get the results, and we provide you some report about this specific data. It's not, of course, a complete project. For this, of course, you need to have the license, but it provides to you a capability to show your management or to convince yourself that the software can help you. It's part of our pre-selling strategy, and we're very happy to have this meeting with you and to generate the results for you. Of course, people that were with us here, again, thank you very much that you were here. I'm always happy to meet you, and we would like to do it again. And we meet you in one web meeting. And we hope that the COVID-19 is going down and will disappear in some way, or we will manage it in a good way, and we will be able to start again to visit companies in their sites, people that are customers, and to generate some seminar in forum people that would like to contact us. Thank you very much. Yeah, I have another question here. How you the ability to model side or bottom mount? Yes, we have. Cliff, we have. It is in the off-center software. We have a capability to have a impeller in the bottom, and we calculate all the hydrodynamic parameters that are controlling processes like VisiMix DR. A side in the wall, we don't have, but at this point, we need always to consult with our R&D people because they always have some idea how to advise what will be the best approximation of it. So if you want to do it, Cliff, please, of course, contact again and we'll do it together. Okay, so it's hard to stop, but we need to stop. So thank you very much to be with us. I will only open my camera to tell you thank you. A pleasure to be with you. I hope to see you again personally, or even if not by this web media. Thank you very much. Have a good time. Bye bye. And take care. Bye bye.